Good afternoon. We start now this webinar. The topic will be a new function in ConSteel version 9 called Frame Corner Wizard, which is a tool for special handling of frame corner zones in the beam model of a framed structure. My name is József Szalai. I will be the presenter today, and some practical information. You can hide the webinar panel with this arrow on this red field, and you can ask question at the end of the presentation by typing it into the chat box. This webinar is the last one of the ConSteel summer webinars, which was about the crane loads, metallurgical loads, and now the corner frame. All of them are new functionalities in the ConSteel new version. And what will be the content of today's short presentation? First of all, I would like to review just very briefly the mechanical behavior of frame corners. What are those special needs which are very important to take into account when we design a framed structure, and why we developed this special tool for handling the frame corners. And then I will review the proper use and the effect of using this frame corner wizard function. First, starting with the modeling, what are the effects on our structural model? Then what is the effect on stability analysis, on standard checks and connection checks, and on the plastic hinge analysis. These are the fields where using this function will have some effect. So I would like to start with two types of frames, hinged frame and a tapered frame. To review the special behavior, I built these frames from shell elements, plates here, as well as from beam elements. So this is the classical beam model for this hinged frame, using some AGA section for the column, IP for the beam, and some hinge here, and it is fixed at the bottom, and we have some top flange restraints perpendicular to this frame. So this is a usual frame model in ConSteel consisting of beam elements. So these are beam. This is a line model. And this is same for tapered. So this is a tapered member with initial height of about 1 meter to 300 millimeters, and again fixed column base and perpendicular supports. In this case I applied a bottom support here in the middle of the beam as well. So to review what's happening here really in the corner, or what is the effect of this corner, I built these two models from plates as well. So this is for the hinged frame. Of course, in the Shear model, I have to consider something for this frame corner zone, something connection or stiffener. So I applied at the top a stiffener, and here at the bottom flange a stiffener as well. All the other dimensions are completely the same as it is in the beam model. And for the tapered frame, I prepared two versions. The first is just end plate connection and stiffener here and here. And the second one, so it is not stiffened more. And the second one is more stiffened by a shear stiffener, a diagonal shear stiffener here. The loading is just in both model, just vertical loads, and in the hinged frame I applied also horizontal load as well, and all the loads are placed eccentrically to the top flange in the beam model, and of course it is here as well, and it is the same in the tapered and Shear model as well. So first let me review the hinged frame. So I run the analysis, and this is just the first order deflection of this frame. The deflection, the maximum value is about 96 millimeters, and it is quite the same as it is for the beam. It is 94. So we can guess that that the loads and the stiffnesses are quite good in plane. Of course, the frame corner has mainly effect on the out of plane behavior now. Considering the stability, we can see that the in-plane behavior is quite good here. And this is now the shell element model. Even in the in-plane behavior, of course, we can see that the behavior of this frame corner zone is a little bit different than the beam elements. We can see here a classical beam with this curvature along the reference line, causing the most dominant internal force, which is the bending moment in this beam. And it is the same for the column also, the curvature and the bending moment. These are the dominant factors affecting the behavior. Now the frame corner zone is a little bit different. This is, we can see that this is a stiffened box with a shear area here. So here the dominant affecting force is shear force, and here and in the other as well. And if we see the tapered frame, we can of course see very similar behavior. So we have here a shear box area, and this area is different. In the beam model of, for example, this hinged frame, the beam end is at a theoretical node, which is a non-existing object, and also the beam, the column, top column end is this theoretical node. So the connection is here, which is somewhere in inside of this shear box, and the peak bending moment in the beam and the peak bending moment in the column also is calculated at this node. And usually this area and this node, these cross sections here are the dominant cross sections of our frame model. So usually the highest bending moments, the highest utilization is here at these cross sections of the beam and the column as well, and it is also very affecting area of the out of plane behavior, so the lateral torsional buckling behavior of this frame, because these are the highest bending moment region producing the lateral torsional buckling. And of course in reality at this zone, so here the cross sections are, first of all, can be different, and secondly the behavior of these cross sections are completely different as it is calculated in the beam model. So up to this point, as I mentioned, the column is a beam-like behavior, but from here the bending moment effect is negligible, and it is rather a shear box area. So that is the main problem, what should be solved somehow or should be treated somehow in a modeling way. There are many proposals how to handle this. In ConSteel, up to now, this area was just handled like here. On the safe side, we calculated a very high bending moment, and if the covering areas are not too high, maybe this bending moment is good for design purposes of these cross sections. And also the lateral torsional buckling, so the stability behavior of these frames are also calculated by considering a continuous connection here at the theoretical node between the two beam elements. So this line and this line. And if we see now the stability behavior, let me show you the buckling behavior of this, first of all, of this hinged frame. So what we see is a classical lateral torsional buckling about the restrained axis, which is on the top flange. So the bottom flange is going out of plane, moving out of plane, and that is what we can calculate, of course, with the beam model. But what is very important, that what is the elastic critical load level in this frame? Built up from shell elements, the calculated elastic critical load level, load factor, is 1.61. And if we see the same result from our beam model, so this is the beam model, we can see that it is 1.33, so considerably lower. But the dominant is that beam, dominant member, and the shape is quite similar than here. Of course, in a shell element, it is the visualization is different than in the beam element, but the shape is quite different. Here also the lower flange is going out of plane. So the elastic critical load factor is lower. That is on the safe side up to now. So what's happening with our tapered frame? Let me show you the buckling. First of all, if we built it from a shell element, it can happen like now if we use very thin or slender plates. Then the first eigenshape, the first buckling shape, is some kind of local buckling. Like now, this is a typical shear buckling of this shear field here, of this web area. That is also an evidence that maybe a local problem, not a global buckling. So let me show you the first buckling mode, which is connected with the global mode, and that is this mode. In this case, the dominant members are the columns, because I applied this special support at the middle here. So the columns are the dominant. The inside flange is buckling, going out of plane, and the elastic critical load level is 2.5 here. And if we see the other model where I applied this special shear stiffener, which is exactly to reduce this local buckling effect here. If I see the buckling mode, what we can see that now the first mode directly the global mode, so those local shear buckling modes are eliminated effectively by this shear stiffener, and this is the first mode, and even the associated elastic critical load factor is much higher, so it is 3.23 now. So this shear stiffener not only affecting the local buckling, but the global buckling as well, because it makes even more stiffer this frame corner zone. This is very important, that of course the global behavior depends on the frame corner configuration. What is exactly the frame corner connection? Now, what are the results of the beam model for the same model, for the same structure? If we see the buckling results, we can see that the basic mode is still the buckling of the column, but again at a lower elastic critical load level. So what is the reason for this? The reason is there can be much more reason, of course, but the basic reason that if we see, for example, this hinged frame, the real connection between what are the most dominant parts now for lateral torsional buckling? The most dominant parts are the inside, so the lower flange and the inside flange of the column. These are the compressed flange area, and in the hinged frame the beam is buckling, but the lower flange, and in this model the column is buckling and the inside flange is going out of plane. So this is the dominant area, and what we see that the real connection in this tapered, if we see the shell element model, the real connection of these flanges somewhere here, and these are really connected even for this unstiffened case. So these are connected here, and in the beam model the column is going up to this point. We can see that the column line is going to here, and there are a huge eccentricity from the theoretical node of the to the compressed flange, and these compressed flange can be rotate not freely but more freely than here. So it is not connected, the compressed flange in the beam model, to the compressed flange of the beam and column here. It is not treated in this beam You can see it is moving almost independently, and the connecting node is very far from the real connection. So this is the main problem, that the theoretical node, and it is the same here, that the theoretical node is not representing well the real connection, real behavior of this frame corner. And that is the main difference between the behavior of the frame, of the beam model and the Shear model, or we can say that the Shear model is closer to reality. So that is a main disadvantage of this beam model. But fortunately, it is calculating on the safe side. So it is producing softer behavior, softer stiffness, and producing a lower elastic critical load level in all the cases. So, and at least we can calculate something, and these are not really far from reality. So these, especially when we have a hinged frame, the difference is not really high. And on the safe side, but we can improve this behavior. And how can we do this? Now I would like to show you the use tool. This here, frame and push apply, and then we see that the frame zones if we push this button. The program selects all the frame, selects all the frame corners, and there are three main conditions for finding the frame corner. Of course, it seeks for the connection of two members, two straight members. The cross-section of the construction, this is the first condition. The second, one of the members should be perfectly vertical, so it should be column. So if I have a leaning column or two beams, then in this version it is not identified as a frame corner. So frame corner is between a column and a beam, and the column should be perfectly vertical. This is the second condition, and the third condition is that the plane of the webs of the two cross sections should be in the same, should be identical. The plane should be identical. So the webs are in the same plane. So these are the three conditions, and if the program finds such frame corners eligible for these conditions, then signified with this graphic. That means that this is a frame corner, what we found here. It is the same for the tapered member. Apply, and here. What are the distances? The distance is, of course, the intersection of the inside flanges by the reference line, here and here as well, and here also. So intersection of this inside flange by this reference line, inside flange by the reference line. This is what we call frame corner zone here. a very important effect, then we can see here, if we see this hunch, the hunch is replaced to the exact position. So if we do not apply this frame corner, I just have to take off, apply, and we can see originally the hunch is starting from the theoretical node from here, but the reality that the hunch is starting from here, from the inside flange of the column, because here we have the cross section. So that's why if we apply this French corner wizard, the hunch is moving to the right place. Here we have this gap just because of the graphic. So this is the first cross section here where this hunch is applied with the appropriate defined height. And of course in this way the length is also not the length but the position is changing, so the end of the hunch will be further from the theoretical node. We can see if I take it out, the end point is closer to here. So in modeling, this is a more realistic modeling possibility for the hunches. For tapering it's not really it's not disturbing the geometry. And what is more important, that what will be the effect of this frame corner in the analysis. We have to recalculate the analysis, and of course in the first order result there will be nothing no change. Or the bending moment diagram, the in-plane deformation is the same, but what's happening with the buckling? What we can see that the buckling mode is quite similar, the shape, but we can see an increase in the elastic critical load factor, which is now closer to this more accurate load factor here in case of this hinged member. What's happening for tapered? Tapered member, again, if I recalculate this was earlier, recalculate with this frame corner zone. Now it is much higher, so the effect is more pronounced here, and this value, this 2.97 elastic critical load factor, is somewhere between the unstiffened, which is 2.5, and the full stiffened, shear stiffened, which is 3.2 value, somewhere between. So we can see that this frame corner wizard giving an effect to the frame corner, that this corner is a little bit more stiffer than we considered earlier in our beam model. How it is achieved? Inside, what's happening? What is happening is that in the finite element mesh, at the end of the frame corner zones, so at this point of the beam and at this point on the column, special finite elements are generated here. So at the frame corner zone, what is generated by the frame corner wizard, and these elements, these finite elements, are neglected from the stability analysis. So it is the same if we calculate a complex model using the partial model analysis for stability calculation. So in this special automatic partial model, only the beam from here and the column from here is considered for buckling analysis, and this frame corner is neglected. And it is the same for here and same here. And if we neglect, that causes increase in the alpha critical value, of course, because the peak bending moments are in this region. But as we reviewed, these bending moments are not realistic. These bending moments are not calculated in the real peak cross-section, which is usually at the stiffeners and at the real position of the end plate. So that is the idea for this frame corner wizard, that we left out from the calculation the bending moments and internal beam-like internal forces of this frame corner, and only the stiffness is considered here. So it is the same, the procedure is the same as it is used in the partial model analysis. And the result, we can see that the corner is stiffer, and that's why the alpha critical value is higher. We can see that in the tapered frame it is considerably higher, and in the hinged frame it is a little bit higher. This difference is depending on the buckling shape, of course. So in this model we can see that the dominant part of the buckling shape is somewhere here in the middle, of course affecting this value. So this modeling here in the corner, but somewhere here we have the dominant region. So not directly affected by the frame corner behavior, but of course it has some impact. We can see the increase from 1.33 to 1.45. In this case, we can see that this is the column is moving right here, also in the frame corner region. So the frame corner is much more has an effect on the buckling mode than in the hinged frame, and that's why if we left out this corner from the bending moment calculation, from the stability calculation, it increases higher the elastic critical load factor. And also in the compared to this value, we can see other effects as well, what cannot be taken into account in the beam effect, like that in this frame corner we have some kind of local buckling together with the global buckling mode that makes softer this frame corner area. But if our frame corner is efficiently stiffened, like here, then of course the real value is still higher than it is the case for hinged frame. So what we can say, that if we have applied this frame corner wizard for the frame zones, it models a sufficiently stiffened connection between the two members. Usually for hinged frame it is enough to use stiffener, horizontal stiffener on the column, but for larger cross sections like here and for slender webs, it is very usual that additional stiffeners are used in order to neglect the local buckling effect, and this is like here the shear stiffener, and in this case this is the case where the frame corner wizard gives quite good result. So this is for stability calculation. If we go on with this hinged frame area, I would like to show what is the other effects on the stability check. If I now take out, just to see the difference, this frame corner zone and run the stability check, or cross sections check. Sorry. Okay, I have to run again the analysis. And now the checks. So we can see that, of course, this area is again the dominant for utilization. The corner is completely not adequate. And of course, the dominant point is here at this node. And it is also not realistic because, as I mentioned, in this area, we don't have this very high peak bending moment. It is negligible here, the bending moment. The highest bending moment is somewhere here in the column and here in the beam. This should be taken into account when we evaluate the cross-section resistance or the buckling resistance as well, based on the slenderness calculation at each cross-section. So now it is not adequate. What's happening if we use this corner wizard, run again the analysis, run the global checks, we can see that the highest utilization is considerably lower, and this area, this zone area, is left out from the global checks, from the utilization calculation. So only those cross sections are evaluated which are really outside of the stiffened connection area, this frame corner zone. And what can be now the solution for this frame? Of course, if we apply here just to prevent the buckling of this beam, we can apply here an additional support at the bottom flange. And run again the analysis. See the global checks. And now it's completely adequate here. But it can happen that for the column, it is, if I don't apply this frame corner, maybe in the top of the column, my cross section is not adequate. But it can be neglected from the calculation. So it can lead the engineer to a more realistic consideration of this frame corner zone in the stability calculation, and we can achieve more economic result taking out these frame corner from the cross-section checks. And where this area checked, this area is, as I mentioned, this shear area is checked in the connection design, because the one of the components which are evaluated in this type of cross connections, beam to column connections, one of the components is the shear in the column web, taking into account the possible stiffeners, shear stiffeners, or just upper lower stiffeners, all the effects which affecting this behavior is taken into account in the connection design, and it is enough and adequate for the checks of this area. We can left out from the cross-section checks. And if I take now connection to, so I identify now, just quickly creating a connection here, a beam to column connection. Maybe I take there the stiffeners, and place back to the node here and here. It is not adequate, but the point is that the bending moment, what we see here, is not a bending moment at a theoretical node, but the real bending moment acting on the end plate. And this is really makes the connection design easier, makes it easier to be an adequate connection design. So at this point, the bending moment is changing very rapidly. So if we have a very high depth column, then the difference can be very considerable between the theoretical node and this point where we have to calculate the bending moment. And using this frame corner wizard, the identified and placed cross-section automatically receives this bending moment. So this is 319, and if we see in the analysis, the bending moments, here we have this 390, and the peak value is about 335 here, and here 345, and what is applied to the connection is 326. So even in this case, they are quite close because the column is not so high, a web column, but there are considerable difference, and this realistic bending moment is applied to the connection design. And the last thing is the plastic hinge analysis. If we have to run a plastic hinge analysis, the plastic hinge can be formed where we have the highest bending moment utilization. And if we don't have the frame corner, these utilizations are usually at the node. So the plastic hinge is here at the node, but this is not realistic and not practical. The practical plastic hinge, for example, in case of this hinged frame, is, for example, here, just below the hinge in the column, and not here. So if I run now without this frame corner plastic hinge analysis, just the first order plastic analysis, we can see that the first is here at the top of the column. So this is not a realistic place for a plastic hinge. And the load factor is 1.34. Second is here again at the top. The third one is here. This is a double plastic hinge. So these are not realistic because this is a theoretical node. Of course, we have to concentrate on this cross-section where we have the highest bending moment. So if we apply frame corner, it will have a realistic plastic hinge design. So we can see that the first stage is now here, because here the bending moment is considerably lower, and it is the first stage at the end of the hinge. It is also very common. The second one is here, the other third one is here. So at the bottom of the hinge region, this is the realistic place for the column. So again, this frame corner is left out from the possible position of the plastic hinges. And these are the realistic plastic hinge calculation. Okay, so I think these were what I wanted to show you. I thank you very much for your attention. I hope that it was a useful presentation for you, and this frame corner wizard will be a useful tool for your everyday design. So thank you for your attention and goodbye.